Welcome to class, everyone. I am absolutely thrilled to have you all here for today's explainer. Let's just jump right in, shall we? Have you ever wondered what causes those breaking ocean waves to glow from within at night? It's not magic, I promise. It's actually millions of tiny, free-floating, single-cell marine organisms called dinoflagellates. And what they're doing is actively converting stored organic energy into this stunning bioluminescent light. It's a gorgeous, highly visible example of exactly what we're going to be covering today. Because we're going to establish the living cell for what it truly is, a miniature, incredibly highly regulated chemical factory.
Okay, so let's take a quick look at today's syllabus to map out our molecular journey. We've got 5 key modules: the cell's chemical factory, the laws of energy, free energy and ATP, enzymes speeding up life, and finally, controlling the chaos.
All right, let's kick things off with our very first lesson, the cell's chemical factory and navigating metabolic pathways.
So, you hear the word metabolism a lot, right? Well, the totality of an organism's chemical reactions is what we call metabolism. Think of it like this massive, elaborate, intersecting roadmap that manages all the material and energy resources of the entire cell. Literally every chemical product your body needs is either built or dismantled along these busy roads. And there are 2 main avenues you can take here. On one side, we have catabolic pathways. These are the downhill, degradative processes. They break down complex molecules into simpler ones, and they release energy along the way. Think of cellular respiration breaking down the lunch you just ate. Now on the other side, we have anabolic pathways. These are your uphill biosynthetic reactions. They actually consume energy to build complicated molecules from simpler ones, like synthesizing a complex muscle protein from basic amino acids. And really, the fundamental secret of the cell is right here. The energy released from those downhill catabolic reactions is stored up and then used to drive the uphill anabolic reactions. Moving right along to Lesson 2 on our syllabus, the laws of energy and thermodynamics in biology.
Because to really grasp metabolism, you have to understand energy, which is simply the capacity to cause change. To make sense of energy transformation, we need to look at its 2 primary forms. Imagine a diver climbing up a high diving platform. As that diver uses muscle movement to climb up the ladder, they are building up potential energy. That's energy that matter possesses simply because of its location or its structure. The higher they climb, the more potential energy they have. But when they leap off that platform, boom! That potential energy is instantly converted into kinetic energy, the energy of motion, which then transfers to the water with a massive splash. In biology, it's the exact same concept. The chemical energy stored in your food is just potential energy waiting to be converted into kinetic energy so your cells can actually move and function.
But there's a catch. There's a cosmic tax on all of this, governed by the second law of thermodynamics. You see, during every single energy transfer, some energy becomes completely unavailable to do work and is just lost to the surroundings as heat. And this increases something called entropy. Entropy is basically a measure of molecular disorder or randomness in a system. Think of a messy room. Without you actively putting in the energy to clean it up, that room naturally just becomes more and more disorganized, right? Well, the universe works the exact same way. There is an unstoppable, relentless trend toward randomization.
Which naturally brings us to our third lesson, free energy and ATP, and how we actually fund all this cellular work.
We really need to understand how the cell manages to fund this constant uphill battle against entropy so we can stay alive and organized. Because listen, if a cell ever reaches thermodynamic equilibrium, it can't do any work. And if it can't do work, it dies, period. So, let me pose a question to the class here. How do we actually know if a chemical reaction will just happen on its own without an input of energy? To figure this out, scientists use a concept called free energy, which is represented by the symbol delta G. Measuring the change in free energy is what lets us predict if a process is spontaneous or not.
So, the absolutely crucial point here is classifying reactions by their free energy changes. First up, exergonic reactions. These proceed with a net release of free energy. Because they are losing free energy, their delta G is negative, which makes them spontaneous. But hey, be careful here. Spontaneous in chemistry just means a reaction is energetically favorable. It does not mean it's going to happen fast. A rusting car is a spontaneous reaction, but obviously it takes years. Conversely, we have endergonic reactions. These absorb free energy. Their delta G is positive, making them non-spontaneous. They literally will not happen unless they have a source of energy pushing them forward.
And the immediate source of energy the cell uses to drive those non-spontaneous reactions? That's ATP, or adenosine triphosphate. You can think of ATP acting chemically like a really tightly compressed spring. If you look at its chemical tail, it has 3 negatively charged phosphate groups. Now, because like charges repel, these 3 groups are basically crammed together, violently pushing away from one another. This intense mutual repulsion creates severe instability and extremely high potential energy.
So how does the cell actually release and use that compressed spring? We call the process energy coupling. First, ATP phosphorylates a reactant. That's a fancy way of saying it physically transfers one of those energetic phosphate groups to another molecule. Second, this creates a phosphorylated intermediate that is highly unstable and reactive. And finally, this new instability forcefully drives the endergonic, energy-consuming reaction to completion. The cell is essentially taking the explosive breakdown of ATP and using it to forcefully push an uphill reaction forward.
Now, because ATP is consumed practically the very millisecond it's made, it has to be continuously regenerated. In fact, a single working muscle cell in your body right now consumes and regenerates 10 million molecules of ATP per second. Let that sink in for just a second. 10 million ATP molecules per second, per cell. It is literally mind-blowing. That is the staggering reality of human metabolism.
All right, moving into Module 4, enzymes, speeding up life and lowering the barriers.
To really appreciate the cellular machines that allow life to happen at a functional, survivable pace, I want you to consider this paradox. If exergonic reactions are energetically favorable and inherently release energy, why don't they just happen instantly? For example, a solution of table sugar dissolved in sterile water can sit for years at room temperature without ever breaking down into simple sugars. The thermodynamics say it wants to break down. So what on earth is holding it back? The answer is energy barriers.
You see, before any chemical reaction can actually occur, the starting molecules have to be contorted into this highly unstable transition state, so their bonds can physically snap. This initial investment of energy is called activation energy. Think of it like trying to bend a really stiff metal keyring to force a new house key onto it. It takes a significant, hard physical push to pry it open before the key can finally slide on. At normal room temperatures, most biological molecules just don't have enough thermal energy floating around to overcome this activation energy barrier on their own.
And this is exactly where enzymes swoop in to save the day. Enzymes are protein catalysts that speed up these reactions by artificially lowering that activation energy barrier. Let's quickly walk through the catalytic cycle. First, a highly specific substrate enters the enzyme's active site. Second, we get what is called an induced fit. The enzyme physically changes its shape just a little bit to tightly enfold the substrate, kind of like a firm, clasping handshake. Third, the activation energy is lowered as the enzyme actively stresses and bends the substrate's chemical bonds. And finally, the new products are released and the enzyme emerges completely unchanged, totally ready to clasp onto the next molecule.
Which brings us to our final lesson for today: controlling the chaos and regulating the factory.
Now, having a factory totally packed full of lightning-fast enzymes comes with its own unique set of problems. Seriously, think about it. How do we prevent absolute chemical chaos if thousands of metabolic pathways are operating simultaneously? If every single enzyme in your body were just running at top speed all the time, it would lead to catastrophic cellular congestion. You would literally burn through all your body's resources in minutes. So the cell has to be a smart factory. It has to be capable of selectively turning these enzymes on and off.
To manage all this, we have to look at how chemicals can halt these enzymes. First up, we have competitive inhibitors. These literally mimic the natural substrate and just jam themselves right into the active site, blocking it completely, like a fake key stuck inside a lock. Then we have non-competitive inhibitors. These are sneaky. They bind somewhere else on the enzyme entirely, but doing that alters the enzyme's overall shape so the active site can no longer function anyway. Interestingly, many deadly toxins work precisely this way as irreversible inhibitors. For instance, the nerve gas sarin and the pesticide DDT cause death by permanently inhibiting key enzymes in the nervous system.
But cells also use reversible inhibition safely and naturally to control their own metabolism through a brilliant process called allosteric regulation. Many enzymes naturally oscillate back and forth between an active shape and an inactive shape. Activator molecules can bind to an enzyme to lock it into its active form, while inhibitor molecules bind to lock it into its inactive form. And notice how naturally fluctuating levels of our old friends ATP and ADP act as allosteric regulators here. If ATP production lags, ADP starts accumulating. That ADP activates the enzymes that speed up catabolism to make more energy. But if the supply of ATP exceeds demand, the excess ATP binds to those exact same enzymes and inhibits them. It is a perfect automatic balancing act of cellular supply and demand.
Another frankly genius self-regulating mechanism is feedback inhibition. Let's look at the pathway that synthesizes the amino acid isoleucine. As the metabolic pathway operates, it synthesizes the isoleucine product. Eventually, that product naturally begins to accumulate in the cell. Once there's an abundance of it, the isoleucine itself physically goes back and binds to the very first enzyme in the pathway, completely shutting it down. The pathway halts. This eloquently automatically prevents the cell from wasting valuable chemical resources over producing things it already has enough of.
Which brings us to this incredibly profound thought to summarize our entire lecture today. The source text beautifully states, organisms are islands of low entropy in an increasingly random universe. I love that. Through the precise, microscopic dance of thermodynamics, the explosive power of ATP, and carefully regulated enzymes, your cells maintain beautiful structural order. They are constantly fighting back against the universal tide of chaos and randomness. I think it elevates the seemingly cold chemistry into a breathtaking philosophical truth about life itself.
Concluding our explainer today, I want to leave you with one final question, just to bridge this complex molecular thermodynamics to your everyday life. As you picture the highly regulated chemical factory operating inside your cells right at this very moment, what new structures will you build with the energy you consume today? Thank you so much for attending class, and keep exploring the incredible world inside you. Catch you next time.